Hello students, in this video we are going to study the dining philosophers of problem. So this is the third and last problem of a classical synchronization problem, or even you may call it as a third problem of a IPC problem. Okay, so this is an an important, a very important for your exam purpose. So they'll ask for you. Okay, so now, so what is this dining philosophers problem? The dining philosopher's problem states that, so as you can see on a slide here, the dining philosopher's problem is what? It states that there are 5 philosophers, okay, they are going to sit and they are going to share a circular table and they are going to eat and think alternatively, okay. So as you can see here, there are 5 philosophers, okay, and they are going to sit on their particular chairs and they are going to share the circular table, and circular in the center of table they have kept one bowl. It may contain a rice or whatever, noodles, whatever. So now they are going to eat, and what is the task of the philosophers here? They are going to eat that bowl of a rice and they are going to think alternatively, okay. So now what is the problem in this dining philosophers problem? So how they are going to eat here? So 5 philosophers are there and only 5 chopsticks are has been kept here, okay. There is a bowl of rice for each of the philosophers and 5 chopsticks has been kept left, right, okay, adjacent to them. A philosopher needs both their right and left chopstick, okay, to eat. The philosophers needs 2 chopsticks, even left and right, okay. So whenever they want to eat the rice, they have to first pick the chopsticks. So first you need to remember here, I don't have mentioned on a slide that they have to first pick up the left chopstick and then they need to pick up the right chopstick, then he is eligible to eat the rice, clear. So now, so what is the problem here? At any time or at any instant, the philosopher is going to either eating or either thinking. So only two states he or she is going to do. A philosopher is either think or either eat. So a hungry philosopher or a philosopher, the person or the philosopher, if he wanted to eat, then if both immediate left and right chopstick should be available, okay. So in case if both the immediate left and right chopsticks are not available, then he is not eligible to eat the rice, okay. So now, then once he completes eating process, if he completes the eating process, then again he will go to the thinking process, clear. So the dining philosopher is a classical synchronization problem, as I told, and it demonstrates a large class of concurrency control problems, okay. So now what is the solution here, or what is the problem? You got it, no? So whenever the philosopher wanted to eat, his immediate left and right chopstick should be available, and one more thing you need to remember, that he must first pick up the left and then he should pick up the right chopstick. So if one of the chopsticks are already busy with some other philosophers, then he is not eligible to eat that bowl of a rice, okay. So the philosopher, now he is going to wait. So once the chopstick is free, then again he is going to occupy that chopstick, clear. So now, so we'll see the code for this. So as you can see on a screen here, we have declared here the a chopstick of array and it is of semaphore, okay. So we have used here the semaphore to represent a chopstick. So as we have declared here the array, that is the variable chopstick, so the index or the size of an chopstick is 5, because only, as I state, the problem is nothing but they have there are 5 philosophers and 5 chopsticks are available, and each philosopher should get the 2 chopsticks at least to eat that bowl of a rice. So now a chopstick can be picked up by executing a weight operation of a semaphore, and similarly that whenever if he finished eating process, after completing his eating process, then he has to keep the chopsticks in the original places, or okay. So that for that we have to execute here, or we have to perform here the signal operation. So already we know that what weight operation and signal operation are going to, how they are going to work. So initially the elements of the chopsticks are initialized to 1. Okay, initially the elements of the chopsticks are initialized to 1 because the chopsticks are on the table and not picked up by any philosophers. Okay, we don't have initialized the chopsticks to 0 because already the chopsticks has been kept in the on the table. So we have to initialize to 1, or you may call it as whenever we have already worked with the weight operation, right? So weight operation, what it does, it is going to decrease the value of an semaphore. So if I initialize the value of a chopstick initially 0, so if I decrease from the 0, it will be 0. So hence we need to initialize its value as a 1. Clear? So now in the above code, first remember here again, take chopstick of I is there, no, that is for left chopstick. Remember, first weight operation is there, no, that is for left chopstick of a philosopher, and similarly chopstick I plus 1 mod 5 is there, no, that is for right chopstick. Just remember this, I don't have mentioned on a slide or on a screen. Clear? So now in this code, first weight operation is going to be performed on our take chopstick of I. So I is what here? I is what now? I is nothing but initially we have initialized to a 1, means weight semaphore value is now 1. Okay, so 1 means the chopstick 1 has been picked up by the philosopher P1 now. Okay, so now as I told, the rule is what here? The philosopher first always he has to pick up the left chopstick and then he has to go with the right chopstick. So to pick up the left chopstick, we have to first weight operation is going to be performed, that is take chopstick of I. So what is the value of I? I is a 1, so F1 fork or F1 chopstick he has to pick up. Okay, so now to pick up the right chopstick, so he has to F2 or chopstick number 2 he has to pick up. Okay, so now, so how he is going to, or how that weight function is going to be worked here? Chopstick of I plus 1 means I plus 1 means 1 it is, so 1 plus 1 is 2, so 2 mod 5 is what? 2, so he has to pick up the chopstick number 2. So now the philosopher P1 has picked up his left chopstick F1 and right chopstick, sorry, F1 and right chopstick F2. So now he is ready to eat a bowl of a rice or a noodles now. So once he has picked up the left and right chopsticks, then he is ready to eat his meal. Okay, so once finished his eating process, then he has to keep his chopsticks in the original places. So for that we have to perform the signal operation. So in signal operation, what we are going to do? Signal operation, there is again we have to put chopsticks. So put means we are keeping the particular chopstick, so each one which he has picked up earlier. So I is nothing but F1 we have to keep first one, left one, and similarly F2 we have to keep. So once these statements are executed, again he will go back to the thinking process. So this is the common process. Okay, clear? So what is the difficulty, or when the difficulty is going to arise here? So the solution, make sure that no two neighboring philosophers or suppose the philosopher P1 is already busy with the eating processor, busy in eating process. So now we need to keep observe that his neighboring philosophers cannot eat at the same time. So if it happens, this solution is going to lead to the deadlock. Are you getting? Suppose P1 philosopher is already busy with the his forks or chopsticks F1 and F2. So if suppose at the same time P2 philosopher also wanted to eat. So what it does, to eat the rice for P2, even he has to pick up the chopsticks, but already P1 is using his F1 and F2. But when the P2 arrives at that is P2 philosopher again wanted to eat the same rice or that meal, then his left one. So his left one is nothing but the F2. So but already F2 is busy with the P1 philosopher. So if this happens, this process can lead to the deadlock. So deadlock means what here? The philosopher is waiting. Okay, if all the chopsticks or certain chopsticks are busy with some other philosophers, then the particular philosopher is going to keep on waiting, okay, for an infinite of time or for a particular time. That process leads to the deadlock situation. Clear? So how you are going to avoid this deadlock situation? Clear? So how we have to avoid this deadlock situation? The solution of, okay, already I have explained this. So difficulty also I have explained. So how we are going to avoid here the deadlock? So deadlock, there should be at most 4 philosophers on the table that we have mentioned. So how we are going to avoid the deadlock here? There should be at most 4 philosophers on the table, but the problem is what here? Already there are 5 philosophers, but we cannot place the 4 philosophers. So this is not done here. So we have to think here that an even philosopher is P2, P4 like that should pick his. What is the solution to avoid the deadlock here? An even philosopher is, you can say there are 5 philosophers. Okay, so among those we have to choose here the even philosopher. So even is P2 and P4. So even philosopher should pick up their right chopstick, then they may go with the left chopstick. So in this way we can avoid the deadlock here. Or similarly for odd philosophers, first we have to choose here the left chopstick and then we will go with the right chopstick. Okay, so if philosopher picks up their particular chopsticks in this way, then we can avoid here the deadlock. Okay, just remember here that a philosopher should only allowed to pick up their chopstick if both are available at the same time. Okay, a philosopher should only be allowed to pick their chopstick if both are available at the same time. Clear? So this is one of the way how we can avoid here the deadlock in the dining philosophers problem. So last one is what I told, a philosopher should only be allowed to pick up their chopstick only when, for example, already the P1 has chosen his, that is he has picked his F1 and F2, and now P2 wants, that is P2 philosopher wants to pick up their particular chopstick. Then what he does now, he need now F3 and F2. Okay, his left is what now, F2, and F3 is the right one. So already the F2 chopstick has been chosen or picked up by the philosopher P1. Okay, so now the third way to avoid the deadlock is what, a philosopher should only be allowed to pick their chopstick if both are available at the same time. Already we cannot occupy or we cannot reserve here a particular chopstick in the earlier. Okay, so this is how we are going to avoid the deadlock in dining philosophers problem. So in next videos we will see how the deadlock is going to be occurred and how we can prevent it. Clear? Thank you.